Thanks very much for the opportunity to talk about the Janus mission. Janus is a NASA simplex mission. We are going to send two separate small spacecraft, each of which will fly by a binary asteroid and image it in high resolution in the visible and thermal infrared. We also combine a lot of ground observations to supplement and complement the measurements we take in situ during our flyby. So with that very brief introduction, let's talk a little bit more about the mission in general. First off, Janus is a NASA simplex mission, and we are currently in phase CD. So we've been confirmed and are moving ahead very well. We are a ride share with the Psyche Discovery mission launch in 2022. As I mentioned, we will send two spacecraft. Each spacecraft will fly by a separate binary asteroid, and those flybys will occur in the first half of 2026. The total budget of the mission is capped at less than $55 million, and we're appreciably below that cap right now. So we have a very focused science team with a lot of experienced researchers from past missions and from a ground observation perspective. I'm the PI, the deputy PI is Jane McMahon. We are both at University of Colorado, which is also where the contract runs through. We have the mission oversight. We're working closely with Lockheed Martin, which is doing the project management, spacecraft build, and mission operations. And we work very closely with Malin Space Sciences, who is providing the instrument suite for the Janus mission. So let's sort of look at what the Janus mission is in a nutshell. This is the first time we've presented since we've been confirmed, so we can give a sort of a complete overview of what it is that we plan to do. So first off, this is representative trajectories of our two spacecraft. And again, we launch with Psyche, and we're actually get placed on a 1.5-year orbit. And in 3 years then, after 2 orbit periods, we come back and we have Earth gravity assists. The two trajectories for our spacecraft are very similar during this time period. They get set up a little bit differently, and then at the Earth gravity assist, we actually get scattered into one of the flybys that goes by the binary asteroid 1991 VH, and the other one which then encounters 1996 FG3. The total cruise is about 42 months, and the flybys for VH occur anywhere from March to January of 2026, and for FG3 anywhere from March to April of 2026. So our target binary asteroids really make us what I think is a great mission. So they're both binary near-Earth asteroids, so we know that they've been subject to multiple transitions through their lives in order to end up in this binary asteroid phase. They're distinct systems. They're different types. VH is an S-type. FG3 is a primitive C-type. However, they also have a lot of similarities with each other, similar shapes, roughly similar sizes and the like. And that's detailed in this little graphic here. They've also both been extensively characterized by ground-based observations, photometry, astrometry, of course, and then radar from Arecibo and from Goldstone. And that means that we know very well where they are in terms of an ephemeris error. So it makes them very feasible targets for flybys. And of course, they're both potentially hazardous asteroids, which also makes them quite interesting to the community and to society in general. So each of the flybys that we carry out will have a pretty similar cadence, and we'll take similar information on both of those. First off, as we are approaching and then departing from our binary asteroids, we will take a single pixel photometry of these systems in order to very precisely time the orbit location, the orbit period, and also sync up the shape of the primary and the secondary for our targets. That will then we'll go through the visible the closest approach phase, where we will actually track. We have very small spacecraft, so they can nimbly turn and track the binary system as we go through closest approach. The distance here will be on the order of 70 to 80 kilometers. And as we go through, we'll get a range of phase angles and a range of resolutions, getting up to better than 800 by 800 pixels across the primary at closest approach. We also have thermal infrared observations throughout this whole closest approach phase, which will be able to determine the temperature distributions on both the primary and the secondary bodies. The instrument suite that we're flying has a very high heritage and proven performance. It's provided by Malin Space Science Systems, and it really consists of a visible imager, an infrared imager, and then associated with this is a DVR, which runs the imagers and also can perform a lot of sophisticated operations. Specifically, we are able to do onboard data compression and selected window downloading using this DVR device. And that's actually enabling for us, since one of our flybys has a relatively low data rate after our closest approach. So that was sort of Janus in a nutshell. Let's look a little bit closer at our mission science goals in order to close out this presentation. The first question you can ask is, why are we interested in studying binary asteroids? And they're actually quite compelling. As you've seen with the previous talks, there are several missions that are being focused on binaries right now. First of all, binaries are ubiquitous in the asteroid population at about 15%, and this holds from NEOs through to the main belt and across the full size distribution as well. We believe the smaller binary asteroids form when we have Rubble pile asteroids that are fission due to high spin rates, probably or usually caused by the Yorp effect. We also know that this is just one of several pathways that these small Rubble pile asteroids can travel down. So by understanding what causes a binary asteroid to form instead of it ending up in some other configuration, really will give us insight into the geophysics of microgravity aggregates. And these are particles, properties that are really ubiquitous throughout the solar system. And the Rubble pile asteroids really give us a key gateway to understand their properties. This is a bit of a busy chart, but Rubble pile asteroids are busy objects. What we're really outlining here is a partial view of Rubble pile asteroid life cycles. And we start with a Rubble pile that's formed from some other cataclysmic impact or disruption that occurs previously. And the Yorp effect will cause these to spin up to the point where they fission. And then depending on how they fission, there are a variety of different outcomes or life cycles, if you will, that they can go through. The one that we're really focused on is this lower one, which is the creation of binary asteroids. And in fact, we know from the process that there has to be a period of chaotic dynamics, a period of dissipation. There has to be a contracting binary Yorp effect, and eventually you can end up with systems in a very stable final state. So the great thing about Janus is that we're actually sampling two different binary asteroids that are at different points along this evolutionary pathway. The first one, 1991 VH, is currently in a chaotic orbital evolution phase. Its secondary is not spin synchronous, with its orbit. And we want to probe why this is the case and better understand this aspect of the overall evolution. The other one, 1996 FG3, has been documented to be in a stable end state, extremely stable. It's not expanding or contracting, meaning that the binary Yorp effect is balanced by the tidal expansion that goes on inside of this body. So by looking at these two different asteroids, binary asteroids at different phases of their evolution, this will also give us key understanding about these bodies in general. So we have we're really four main objectives that are split up into two main goals. The first goal, which has two sub-objectives, which I'm not talking about here, is to really answer the question, how do binary asteroids form? And the way we will do this is by taking imaging, a relatively high-resolution imaging that will give us morphology of these binary asteroid systems, which in turn will give us insight of formation and really will allow us to test different hypotheses for how these binary asteroids form. And I've thrown up at least three hypotheses here. There are additional ones, but they range from having a very strong interior for rubble piles so that you have surface flows of material that go out and then accumulate in orbits. It could be a multiple component body originally that fissions and ends up with, into a binary asteroid system. Or it could have a rubble pile with a very weak interior that has an internal failure, which then ejects material into orbits, which then settles into a stable orbit phase. So these are just three examples. And by taking detailed morphology, we'll get this insight. The second goals are really specialized to these specific binary asteroid systems. The first one from 1996 FG3 will really take advantage of this being the most precisely measured NEO binary. First of all, it's a primitive C-type, so similar to Ryugu and Bennu in composition and shape, and it lies in this binary Yorp tide equilibrium, meaning that it's extremely stable and predictable orbit. So by doing our thermal mapping, we'll be able to constrain the binary Yorp coefficient for this body, and that will give us constraints on tidal dissipation inside of the primary. And then the second one, asteroid 1991 VH, the secondary is not in a synchronous state, and in fact is in a chaotic rotation state, and the orbit itself even jumps around chaotically. So by taking our measurements, we'll be able to better understand this particular system and understand why it is currently not in a settled state and test various theories or hypotheses for why this is the case. So to end up, Janus is confirmed and is currently in phase CD. We are on budget and on schedule. We will provide the first high-resolution scientific observations of multiple NEO binary asteroids across a full range of phase angles. By doing this, we'll provide insight into the mechanics of rubble pile bodies, into microgravity geophysical processes in general. We're also excited because Janus defines a new spacecraft and mission profile that can provide a responsive scientific and planetary defense capability for NEO characterization. And finally, we're ready and able to serve as an inaugural member of NASA's Simplex program. So with that, if there's any time, I'd be happy to take any questions.
Thank you, Dan. There is time for a few questions. So if you want to type it in, you have a minute. I did have a Tom has a question. Tom Statler, for how many orbital periods will you have resolved imaging of 91 VH?
So we only have resolved imaging through closest approach, which is fast enough so that we don't, the system does not go through full cycles. However, on approach and on departure, when we have a very good viewing aspect where we can take photometry over multiple orbits as we come in and as we go out. What that does is it helps tie down where the system is at an earlier epoch and at a later epoch, and then dynamically we'll be able to fit the entire system dynamics through the orientation that the system has when we go through our closest approach and get our higher resolution imaging.
The next question is by Nancy Chabot, who asks, what have been the main challenges of an exciting mission like this in simplex?
Yeah, well, if you're experienced with NASA missions and you saw the budget number, you realize that it's not a very big pot of money. So, but the way that that's mitigated is that we're also classified as a Class D mission, which means that we don't have to have the same level of guarantees and redundancies as, say, a Discovery mission or a New Frontiers mission needs. Part of the challenge has been helping NASA develop what are the proper protocols as we go through and develop a Class D mission. How do we take more risk into the overall system without, with still having a firm guarantee in our minds that we'll be able to achieve our goals. So I would guess that's probably one of the main challenges that we're addressing, but it's also very exciting to not have all of that overhead, if you will, that you get with a higher class mission.
You have several questions, so I'm going to ask one more question, and then you might have to go back to the chat and write to the people who have other questions. Paul Abel asks, can you talk about how DART can lead to any insights for your mission?
So DART happens a couple years before ours. We will certainly look at the images that we get from Didymos and see if they have any direct implications for how we're modeling our system and the like. I'm also a member of the DART team, and that's been fortuitous because we've developed software for modeling binary asteroids in part under DART support, but that's also now supporting our work in Janus. So there's a couple different ways in that we're leveraging the DART mission.